Okay, so Fourier series. So I'm very excited to tell you about Fourier series because it's one of the most important techniques in applied mathematics. And not just applied mathematics, but mathematics in general. Because like some of the best techniques in mathematics, it attempts to represent something possibly quite complicated as a sum or combination of things that are very simple. And this idea works in mathematics, has worked in mathematics over and over again. For example, the technique that really made calculus happen in the hands of Newton is to represent all functions as polynomials. Now you had to make a compromise. You had to make the polynomial be of infinite degree. So it became an infinite power series. And that was Newton's breakthrough that allowed him to make calculus and many of the ideas that have been simmering before Newton. He was able to use that insight to turn all of those ideas into a consistent and robust technique. So that was the calculus breakthrough. And I think it's a very unexpected breakthrough because why would you ever think that the sine function can be thought of as a polynomial, or the cosine, or the arcsine, or the log, or the exponential? So it took quite a bit of imagination, and there was a leap there to realize that yes, all functions, more or less, can be represented as power series. And what's the beauty of power series? Each individual term is simple. Fourier series has a similar essence. It attempts to represent something very complicated in terms of things that we think of as simple. We will try to represent this general function f of x, which may look like this, and I chose a nice one. We'll choose it on the segment from minus pi to pi, and that's arbitrary just to make numbers work out a little bit more neatly, but it can be on any segment. And we will want to represent it as a sum, and we'll have to say infinite sum, of sines and cosines. Very much in the spirit of mathematics, and also very much in the spirit of linear algebra. In fact, I would prefer to deliver this lecture in the context of linear algebra. And I will get a chance in our linear algebra class a couple of weeks from now to actually do that. And so I'm actually very happy that I will now get a chance to talk about this without putting too much emphasis on linear algebra, so that when later I do it from the point of linear algebra, you can contrast the two approaches. And you will see some of the nitty-gritty details now, but you will not see the framework because I won't emphasize it. And it's also very nice to have a lecture that doesn't just say this is obvious from the linear algebra point of view, which it will be. Once we impose the linear algebra framework on the ideas that I'm about to share, everything will seem simple and inevitable. Everything right now will seem like, oh, it's working out just right, almost by accident. So that's what makes this nice and a good opportunity to do it. It's not always that you get to talk about Fourier series not in a linear algebra context, because ultimately it's a linear algebra problem. Okay, so that's our goal. We're going to represent this function as a sum of sines and cosines. Is it possible? Would you intuitively say that it's possible or not? Well, let me ask you this question again in a few minutes. But first I want to narrow down our sines and cosines. These will be sines and cosines that fit perfectly and periodically within this segment. So sine of x starts right here, ends right here, and is one period. Then the next sine will be sine of 2x, sine of 3x. So sines and cosines whose periods are fractions, not just fractions, are 1 over n fractions of this segment. So very few sines and cosines. That's what will make it a series, a discrete sum. And when did these sines and cosines come from? Well, we saw them in the previous lecture. They arose as eigenfunctions of the Laplace operator. Is it a coincidence? It's not at all a coincidence. That's actually the greater truth. At first, you might say sines and cosines are nice, but why sines and cosines? Why not a mixture of sines, cosines, and exponentials? Why not a mixture of sines, cosines, and polynomials? Seems like a more flexible approach. Throw more in, make it richer. Well, it turns out you don't need to do it. It turns out that sines and cosines are enough. The word that's used in analysis to describe this situation is complete. And their completeness has everything to do with the fact that there are sines and cosines of the Laplace operator. And you might take it a step further and ask me, well, what's so special about the Laplace operator? And that's a very, very valid question. Where did the Laplace operator come from? You kind of postulated it on intuitive grounds. Yes, I did. But there is something special about Laplace, the Laplace operator, not so much as to make it exclusive. This idea that you can take an operator of a certain kind and its eigenfunctions will be a complete enough set to decompose any reasonable function you can come up with on the same domain is a more general idea. There's a whole category of operators like that. And that comes out of variational principles having to do with minimization and so forth. So another fascinating topic which we will leave out completely. So here's how I see the history. They did separation of variables. They realized that sines and cosines are these very special functions that arise as solutions to equations once they're separated. And then the question was very natural. You have arbitrary initial conditions, and the method naturally calls for those initial conditions to be decomposed with respect to sines and cosines. And so that question was being addressed without linear algebra. And then I think people noticed it all was very organic. It just becomes, apparent that that's the part that you should focus on. That's the part that counts from a certain point of view. From another point of view, it could be something else that matters. And so over the years, there was great debate as to whether or not this is even possible to decompose every function as what will be called a Fourier series, a linear combination of sines and cosines. What is the rigorous theory for it? That gave rise to Hilbert spaces and all of those other wonderful things and much of analysis. And as a matter of fact, set theory. Cantor was motivated by this question of whether it's possible to decompose any function as a linear combination, infinite linear combination of sines and cosines. And his conclusion was no, because there are only countably many, we have to be careful, degrees of freedom in a Fourier series and uncountably many degrees of freedom in a function. Anyway, that's where accountability came from. So, yes, it's a very natural question. We discovered this question on our own. If you think back to the last lecture, I kind of just said it, but I'll repeat it. We discovered that this is the question to be asked because we wrote our function, the solution to our partial differential equation with initial conditions and boundary conditions, as an infinite linear combination of discrete sines and cosines. Those precise sines and cosines, sine of nx and cosines of nx. So that was a very natural question. Okay, and those are the eigenfunctions, as I said, of the Laplace operator. And so those can be interpreted, or their square roots, as the frequencies of the string. And one thing that I forgot to mention last time, and I'd like to mention now, is that that's what makes a guitar string or any other musical instrument, string musical instrument, sound so nice. Because the frequencies that you hear when you pluck a string is the fundamental frequency, then twice the fundamental frequency, 3 times the fundamental, 4 times, 5 times, beautiful natural number, series of natural numbers. And that's what makes the note sound so coherent. When we later study what a drum sounds like by asking what are the eigenfunctions and eigenvalues of the Laplace operator on the drum, which we'll do next time, you will see that they're all over the place. They don't form this nice harmonic series. And that's why drums don't sound like notes to us. They sound like drums.